Animals have a variety of reproductive strategies. Some have few offspring but take good care of them, and others have many offspring and leave them to fend for themselves. So, populations and communities are groups of organisms interacting in the same area. And a population refers to the same species living in the same place at a certain time. And a community is made up of all the different populations of all the organisms that occupy that area. So, therefore, the study of the community involves only the organisms. A population involves only the certain species, but the study of an ecosystem involves studying all of the biotic and abiotic components of an area. So, we're also looking at like the water and the air and the rocks and the minerals and nutrients in the soil. So, the habitat is the physical area where a species lives. So, that's where a species lives. And an ecological niche is a species' role in the community. So, is it a predator? Is it a prey species? Does it provide shelter for another organism? So, its role in the community. And we're going to look at a few more equations today. Again, they're also in your data booklet. So, population size is the number of organisms of the same species sharing the same habitat at the same size. And the population density is the number of organisms per unit space. So, we can calculate this by the number of organisms divided by the area. And it doesn't matter what the area is calculated in. It could be calculated in volume, it could be calculated in meters squared, it could be calculated in kilometers squared. Um, but you just have to make sure your units are correct in your answer. We can compare population densities by determining if there's been any changes in the population over a certain period of time. So if we look at a change in density over a change in time, we can find the rate of density change. So is the density of a population going up or going down? And we can also look at the way that populations change, either they grow or they decrease. So, two ways that a population will increase is by increasing the natality or the birth rate. And this is the number of offspring born in a species in a single year. Immigration is the number of individuals of a species that move into an existing population. So, between natality and immigration, these are ways that a population can increase. Mortality or death rate, the number of individuals that die in a single year, and emigration, the number of individuals that move out of an existing population, are how a population would decrease. So when we compare both of these, we can see our change in population. So the delta N, the change in the number of individuals. We'll take birth plus immigration minus death plus emigration. If our number is positive, the population has increased. If our number is negative, the population has decreased. We can also calculate the growth rate of a species. So if we look here at the Alberta sage grouse, the population was 375 in 1970, but by 2002, the population was only 350. So assuming that it decreased at a constant rate, let's calculate the growth rate. So we're going to take our final population total. So we're going to go 350 minus 4,375. And we're going to divide it by the years. So 2002 minus 1970. And we get an answer of negative 125.8. And rounding that to negative 126. So we would have a negative growth rate because the population of that species is declining. And again, you want to go the final population minus the initial population, final year minus the initial year. So when we're calculating growth rates, this does not always factor the initial size of a population. So the amount of increase in a large population will also be larger than that of a smaller population because there's more individuals that can reproduce. Therefore, the increase is going to be greater. So if we want to compare two populations, we want to do the per capita growth rate. So we want to take the births plus immigration minus deaths plus emigration divided by the original population size. And this will give us the per capita growth rate per individual. So is it growing like by 1.2 per individual? Is it growing by 3.7 per individual? And that will tell us how fast the population is growing. So when we look at mature ecosystems, populations also tend to remain stable over the long term in a state called dynamic equilibrium, similar to how homeostasis occurs in our bodies. So dynamic equilibrium is where our populations are going to adjust to changes in the environment to maintain an equilibrium. If we have a environment that has a high amount of stress because we have increased drought and colder winters, that population might go down. Whereas if then the environment changes to have more rainfall and more mild winters, that population is going to increase. So populations can also be classified as open or closed. In open populations, natality, mortality, immigration, and emigration are all functioning. So animals can move in or out of the population and new animals are born. In closed population, immigration and emigration do not occur, so only changes in natality and mortality are the factors. So kind of a best example of a closed population is going to be the resident whale pods of the southern Juan de Fuca Strait between Vancouver and Victoria. Because they have family pods, typically the only changes in population are births and deaths, because whales very rarely will immigrate from one group to another. So when we're looking at growth curves of a population, we have three different types. One is a J-shaped curve, and this happens in an ideal environment, and it would happen only if relatively few active individuals were placed into that environment at the beginning. So there's unlimited space, food and water, no disease, no predation, and that population can be expected to reproduce at its maximum physiological rate, so its maximum biotic potential. This J-shaped curve has exponential growth, and the only factors limiting the rate of growth would be gamete formation and the survival of offspring. So how quickly can an organism reproduce and how many of its offspring are able to survive. So there's a lag phase at the beginning, followed by a steep increase of numbers once we hit that exponential growth stage. The second type of growth curve is an S-shaped curve, and they show this curve for open populations. So animals are able to go in and out of the population, as well as natality and mortality occur. So we have our lag phase at the beginning, our phase of exponential growth, but then we have our stationary phase. So we've hit the point where we've reached the carrying capacity of that environment. So that stationary phase where the curve levels off is the maximum number of individuals that the environment can support. So now reproduction rate will slow down. The mortality rate and birth rate might match each other quite closely. And the highest possible where we have the exponential phase is still going to be where we have that growth rate meeting its biotic potential. And we're looking at our biotic potential. It's determined by 7 different factors. One is the number of offspring that an organism can have per reproductive cycle. So some like elephants have 1, bears could have upwards of 2 or 3, and then organisms like rabbits have 6 or 7. Other ones, such as insects and fish, have hundreds or thousands of offspring per reproductive cycle. Then we look at the capacity for survival, the number of offspring that survive to reproductive age. And this is typically inverse to the number of offspring. So the more offspring you have, the less likely they are to survive to a reproductive age, where the fewer offspring you have, the more likely they are to survive. Maturity, the age that an organism can reproduce at. So some, like fruit flies, will have a very low reproductive age, where others, like elephants and whales, reach a reproductive age 10 to 20 years after they are born. The number of times that an organism can reproduce in its lifespan. Is it once a year, like ungulates? Is it every few years, like bears? Or is it several times a year, like rabbits and mice? Also, the lifespan of an organism. Does it live for weeks? Does it live for days? Does it live for years? Does it live for decades? And this also occurs along with the procreation, so the number of times an organism can reproduce. Also, the gender ratio. So the more female organisms you have, where there is a lower number of offspring, the more likely your biotic potential is higher, because females can carry more. The more females you have, the more offspring can be born. And then mate availability. So if there is not mates available, it doesn't matter that if you have a low age of maturity, if you can procreate many times in your lifespan, and if you have many offspring. If there's no mates available, your biotic potential will be low. So here we can look at a yearly breeding pattern, like a growth curve. So in the winter, we typically have our lowest levels of population because animals have died through predation, through hunting, through accidents, and through struggling in the winter. Whereas in the spring, we have high birth rates. Then we can see in the summer as maybe some young don't make it through the summer. We have starvation. We just have our general mortality. And then through predation and hunting, our population decreases to its winter carrying capacity. So limiting factors that affect a habitat's carrying capacity are also known as environmental resistance. And there's two general types of environmental resistance. One is abiotic limiting factors, and these are density independent. So they affect members of the population regardless of the population density. So fires, droughts, tornadoes, floods. It doesn't matter if there's two wolves in an area or 500. If a fire comes through that area, it's going to affect them equally. Then there's the density dependent limiting factors. And these are biotic limiting factors. So these are biotic factors that affect a population, and they often have bigger impacts on the population because they occur more often. So this would be things like parasites, whether a disease will spread more quickly in large, closely grouped populations, the role of predation in a population. They all will limit the growth of a population in a certain area. So lastly, we're going to look at growth curves for closed populations because there's limited resources. So at the end of the stationary phase in a closed system growth curve, because there is no additional resources, we have a death phase. And this is where the mortality rate will exceed the natality rate. And again, organisms cannot move in and out. So nutrients run out, waste accumulates, and organisms are no longer able to survive. We'll occasionally only see this in things like algal blooms. As opposed to large mammal populations, for example. So when we look at the biotic potential and different types of growth curves, there's two different types of reproductive strategies. We have K reproductive strategies and R reproductive strategies. K reproductive strategies are typically found in stable environments who are at close to the carrying capacity. So this would be those S-shaped curve organisms. If populations become crowded, we're going to have that intraspecific competition and lots of biotic limiting factors. Typically, if you have a K-selected reproductive strategy, you're usually a large animal and produce young that are slow growing and require parental care. So things like whales, bears, elephants, moose. And you'll have few offspring per reproductive cycle so that you can put more effort into ensuring their survival. Our reproductive strategies happen in populations where they have many unpredictable changes. So usually they're organisms that are very small in size, have short lifespans, and an early reproductive age. There's a very high reproductive rate, and the offspring grow rapidly, but little parental care is needed. So often, not many of the offspring will survive to adulthood to reproduce again. Sudden environmental changes can result in a large number of deaths. So organisms that grow in the summer and die in the fall, like mosquitoes. And often this is a reproductive strategy that's used by bacteria, insects, annual plants, algae, different like coral and fish species that have a lot of offspring that are possibly produced. Now, there are some organisms that don't fall neatly into the R and K category, like if we look at things like mice or rabbits that have many offspring several times a year, but they typically won't have the massive 3,000 offspring that you would see in an R-selected strategy.